let's get started. So, again, the exam will be Tuesday. So next class, it'll be on chapters 3, 4, and 5. So for chapter 5, I decided to just have it on equation, torsion equation, and the angle of twist problems. Okay, so we won't do the statically indeterminate problems. Okay. The exam will be administered in the same way as the first exam, so I don't really think there'd be much different in that. Obviously, questions are different, but I think that's going to go the same way. I'll do a little bit of review and then I'll kind of open it up to questions. But before I get started in the review, is there any logistical questions with regard to the exam? I'll wait while I load up my whiteboard thing. No. All right, so let me go over super quick the material from chapter 3, 4, and 5. If I can share my screen. There it is. All right, so remember chapter 3, right? Oops, chapter. That was on material laws, right? Mostly elasticity. So on that, the three big concepts are Hooke's law, right, where the normal stress is equal to Young's modulus times the normal strain. Now for normal loading, axial loading, we also have this Poisson effect, so we can figure out, the lateral strain is related to the longitudinal strain through Poisson's ratio, nu, right? And the negative sign is there because they change direction. If you extend in the longitudinal direction, you contract in the lateral. And if you contract in the longitudinal direction, you stretch in the lateral direction, okay? Now, that only happens in axial response. But then, of course, there was also the analog to Hooke's law, but for shear, right? So it's, again, just a simple linear homogeneous relationship between the shear stress and the shear strain through the shear modulus G, okay? So again, these are concepts that you should internalize, so you should memorize those, okay? Obviously, I'll give you all material constants, nu, G, E, all that sort of stuff, right? We also talked a lot about the tensile test and inelastic response and that sort of stuff. But honestly, I don't know, maybe I might ask a short question or two on those. But as far as solving problems, remember the flavor of problems we had here were along the lines of, that sort of block diagram where you could be given loads and figure out stresses. And we can also be given deformations and use that to calculate strains. And we use the material law to relate the stresses and the strains, right? So the problems were always along the lines of you'd start somewhere in this block, maybe you're given the force, the axial force, and they want you to figure out the lateral contraction or the diametric change, right? So you have this sort of side bar. Right, where you're able to Oh, that's okay. What about it? I'm great. I can't eat the popcorn. So you start somewhere like load, and then you need to, maybe they ask for the lateral contraction, the diametric contraction, right? So that means you have to figure out the stress, and then figure out the longitudinal strain, and then use Poisson's ratio to figure out the lateral strain, and then you can figure out the diametric change, or could go from anywhere to anywhere on here, right? So you have to be able to, understand these concepts that allow you to navigate this sort of block diagram here, right? So it's not like they're always going to be the same problem. All right. Is there any questions on that? That's the most important material from chapter 3. Right, the linear elastic response. Okay. All right. Chapter 4. Right, these were the axial problems, right? And so for the axial problems, well, of course, from chapter 1, we already knew that the normal stress is the internal normal force over the cross-sectional area. But we extended this a bit, and we were able to get that the elongation is equal to, well, in one sense, the integral of the internal force over the cross-sectional area times Young's modulus, integrated over the length. But very often, N, A, and E are all constant for a particular length, and then this would just reduce to NL over AE, okay? Or more often, you actually see this as PL over AE. But again, don't make the mistake of, to solve, when you have to solve a problem like this, don't just grab the nearest force. Really, it needs to be the internal force that gets exposed by the free body diagram. These are all from those free body diagrams, okay? Always going to be the internal force. All the calculations in this class actually involving stress and elongation will always involve the internal forces, okay? Then we also looked at statically indeterminate problems, right? And remember, we kind of had two major flavors of these, where you had elements in series and also problems where you had elements in parallel. Okay, but the idea here was that we had two unknowns because we have two reactions and we only have one equation of equilibrium. So we have to always supplement this with some particular type of compatibility or displacement condition. In this case, it's that the total elongation is 0. Or in this case, I'm sorry, I shouldn't draw it this way. I should draw this one as follows. Or for this one, that the elongation of the two sections are the same, okay? There were also some other ones where there were gaps and stuff, but they were kind of variants of this, all right? So you have to know how to take these compatibility equations all right, you use those compatibility equations, use the elongation equation to get those in terms of the internal normal forces, which will then allow you to, through free body diagrams, relate those to the external forces. And that'll give you an additional equation that you can use to solve the problems, right? We also talked about thermal stresses. These were, relatively straightforward, right? Where you would figure out, right, that you had some expansion. So you had a thermal stress that was equal to the thermal expansion coefficient alpha times some change in temperature. Now, many of these are pretty straightforward, and you don't have to, you can kind of do them by just thinking about it. But remember also, like with the one with the spring, on the shaft and whatnot, sometimes it gets a little bit confusing as to how to go about it. And remember that we can always use this additive decomposition, that the measured strain, epsilon, the actual strain you would actually see, the change in length over length, is equal to the mechanical strain plus this thermal strain, all right? and if the part is constrained, right, the measured strain is 0, so the mechanical strain equals the negative of the thermal strain. Or if it's free to expand, the measured strain equals the thermal strain, in which case the mechanical strain is 0. Or there was some combination where it would expand a little bit freely, and then the rest would be resisted by mechanical strain. But whatever, the idea here is you actually need to get the mechanical strain, because that's the one that gets multiplied by Young's modulus and gives you the actual stress in the component, okay? Again, a lot of times for very simple problems, like where it's just a bar fixed on the ends and it expands, you just say, okay, here's the elongation, and then it's PL over AE, right? But, sometimes it gets a little more complicated, and this decomposition is kind of helpful for figuring that out, all right? The last thing we did in this chapter was stress concentration factors. And I need to assign the second finite element project based on this. But here, this is pretty straightforward, right? We found out like a peak stress, although we normally just call it sigma, but it's like a maximum stress was equal to, sort of the average stress that we normally would have found, just the straight force over area stress, but it gets magnified by this stress concentration factor, which for us, you'll always be able to get K from those plots. And, depending upon the loading, the geometrical and loading situation, you have different plots. But, in the book, there are only the two cases, the bar with the hole, and then the stepped bar with the external fillets. Those are the only two cases we'll be considering, okay? And that's the material for chapter 4. Is there any questions on that stuff, at least as far as the material? What you'd be responsible for? Like, obviously, I'll give you the curves that allow you to get K. Obviously, I give you those, right? This equation you really should memorize, right? PL over AE, right? And I think that's it. Now, for chapter 5, we're talking about torsion. I forget which sections they are, but we're only going to do the problems where we use the torsion equation, where we figure out the shear stress due to torsion, which is TC over J, right? Or, right? So you should understand how to use these equations. But again, also these are concepts, right? So the shear stress actually changes with respect to radius, right? So it varies across the cross section. At the center, it's 0. Its maximum value is at the outer radius or outer diameter. And it's, as the internal torque increases, the stress goes up. And the geometric factor that resists that is not cross-sectional area, but this quantity J, the second polar area moment, right? And for a circular shaft, right, for any cross-section, it's the integral of the area of rho squared dA. But we looked at this for a circular shaft, it got to be pi over 32 diameter to the 4th power, right? And if it's hollow, you can just subtract the inner diameter from that, so we pi over 32, outer diameter to the 4th minus inner diameter to the 4th, okay? And then the last one is just to be able to calculate the angle of twist, right? Which is T, well, I guess I should do it consistently, right? is technically the integral from 0 to L of the internal torque over J times G integrated over X. But again, just like the axial elongation, if these quantities are constant in the section, we're just left with TL over JG. And again, remember, this torque is the torque, the internal torque that we get from a free body diagram. You don't just grab the nearest externally applied torque to that point, right? Okay. All right, and that's it. Okay, so no statically indeterminate torsion, no stress concentration factors. Okay, so it's actually a pretty fair amount of material. Okay, but I think you could probably imagine, a problem related to chapter 3. Probably I would definitely look at statically indeterminate problems. That's always going to be a very tempting problem to assign. And then something that's rather straightforward with regard to the stress calculation or the angle of twist. These will be kind of straightforward problems, all right? And maybe one out of these two or something like that, if I can squeeze it in, okay? Any questions on that? Again, very much homework type of problems. Yeah, sorry.
For the stress concentration factor, if we're given a problem for that, what would be the best way of calculating? Because you have the circle and then you also have the neck or the fillet, and like for the homework problems, we use the circle, but in a problem.
No. Oh, okay. That's a very good point. So there was the problem where you had the two stress concentration factors at the same time. And you could actually have more than two, right? This is a pretty important concept. You had this and this, right? So of course there's a force here, right? So when you're designing something, every single point has to survive, right? You can't just say, oh, I only checked one part, right? And you don't necessarily know a priori whether the stress situation will be worse at the hole or at the fillet. So you really do need to check both, right? So for this particular problem, I forget, I think it was the stress was higher at the fillet. At the hole, right here. But it could have been that it was higher at the fillet, depending upon the geometry, all right? And you need to check both, okay? And whichever one is the worst, that's the one you report, or that's the one that's going to limit your design, your acceptable load that you can put on the component, right? Like practically on any mechanical component design, there might be like 5, 6, 7 regions where you need to check what the stress state is, right? Obviously, in this particular case, if you can get it to work here and here, it'll also work through this section and this section. But there are other types of geometries where that won't necessarily be the case, and you'll have to check like multiple points. You know what I mean, right? So the answer, just to summarize, it's not that you should check at the hole or the fillet, but you really need to check at both and then see which one is sort of the limiting case, which one gives you the highest stress. And that's the one that you're going to have to most likely use to get your answer. If your answer is like, what's the maximum allowable force P that can be applied, you would use that point, whether it's the hole or the fillet, to determine the maximum load P, right? Does that make sense?
Yes, thank you.
But again, like that's a much bigger concept. That has to do with design. So when you have to design an airplane, right, there's thousands of things that have to be checked. And that's actually not that uncommon of a situation. And to do the design correctly, you really need to make sure all of those 1,000 points, 10,000 are satisfied to have a viable design. So yeah. Any other questions on the basic material? I'll ask if anyone has specific problems they want to do as well, but just on this stuff. Anything in the chat? What's going on in the chat? Chat. Okay, I don't know. I can't see the chat. I don't know what happens when I share screens. Everything gets really weird on my computer. I can't see half the stuff. Okay. All right. Are there any homework problems that people want to have questions on or want to see worked out?
Yeah, in
Oh,
the
sir.
chat. Yep.
Sorry.
Is there something in the chat? Could somebody just say?
Yeah,
'Cause I
Oh,
can't
There's
see-
somebody in the chat that says that they want problems 4.16 and 4.39 done.
Okay.
Yeah.
All right. Anybody want to see any problems from chapter 3?
yes, can you do the 326?
Yeah, maybe we should do one in chapter 3 first. We'll just do that. It's been a while since we did those. And then I'll do the ones in 4. Yeah. What time is it? I got still another hour, right? So I still got plenty of time. Okay. Wait, which one in chapter 3? I'm sorry. What did you say? 326? Was that what you said?
Yes, sir.
Let's see. Find that.
I can't remember if we already did it, but
Well, if you can't remember, I certainly can't. I've been looking at these problems for way too long. Let's see. That's 326. Oh, okay, so that's in the section. Is that like a Poisson ratio problem or something? Oh, yeah, I think I did that in class, right? I think I actually did this one in class, right?
okay.
I can summarize super quick on this one, okay? I mean, that's fine. You know, I won't do all the details on it, but I can give this up pretty quick on this one. Where is my window? Yeah. All right. That's right. So this is a good example, one that you have to kind of go around the block, right? So here you are, what do we got? We are given, so you know, you have the the plug and then the sleeve, right? And there's initially a little bit of a gap. There is a gap of 2 millimeters diametric, right? Right, between the sleeve and the plug. All right, they want you to find out the pressure, how much force P has to be applied till that inner plug expands diametrically that 2 millimeters and touches the outer sleeve. Does that make sense? So find P that gives you a change in diameter equal to 2 millimeters, okay? So again, in this particular situation, what we have is the following, right? All right, so we won't use this branch, but also you could also figure out the change in length, right? But we won't really use that. So, right, there's the force P, but actually this stress is going to equal the applied pressure. So we know what this is, right? This is the 2 millimeters, okay? And we know we're on this sort of Poisson's ratio branch because it's the loading is in the axial direction, and this is a diametric change. It's a lateral change, and the loading is in the longitudinal direction, okay? So obviously it has to involve Poisson's ratio. So we can figure out, knowing how much the diameter has to change, we can figure out the lateral strain, right? That strain is going to equal the change in diameter, the 2 millimeters over the original diameter. All right. We know both of those, so we can get the lateral strain. It's going to be a positive number in this particular case, right? Now, knowing that, right, we need to get the longitudinal strain so we can continue down this path here and get to this point, right? So that's going to be through the Poisson's ratio. So we know that the lateral strain equals minus nu times the longitudinal strain. So this is what we want. So the longitudinal strain is going to equal the lateral strain, this strain, over Poisson's ratio. So that strain actually is going to be a negative number, and its magnitude will be greater than the lateral strain, because it always is, because Poisson's ratio is less than a half. You know what I mean? Now, once I know that, right? So this is actually the strain, although it doesn't matter, but this is how much the plug changes in height. That's that strain, okay? And I don't really care about that. Other than that, I'm going to use that in Hooke's law to get the stress. So the stress in that case is going to equal Young's modulus times that longitudinal strain, right? So that's going to give you, this number here is going to be less than 0. So the stress is going to be less than 0. It's a compressive stress. And I think as we talked about in class, that is equal to the pressure that's applied, right? And if you don't see that, you can get the actual force by multiplying the stress by the area, but then to get the pressure, you take that force and divide it by the same area, so you get back to the stress, except there's a sign change because we use positive pressure as a compressive stress. Okay, does that work?
Yes, sir.
It's a good problem because, again, it shows you this thing of like, I don't know, again, I don't want to beat a dead horse on this, right? But again, when you study for classes like this or any engineering class, in my opinion, again, you want to try to focus on what's the concept and how do I apply that to solving engineering problems, right? Or whatever the problem going to be asked, right? And in this particular case, you don't want to memorize that, hey, when I am given a problem from chapter 3, I multiply by the diameter and then divide by Poisson's ratio and then multiply by the area. You know what I mean, right? You want to think about it in terms of these relationships are the conceptual things that you know. And again, it's not always going to be this same path. It might be something different, but it's really the same problem, So yeah, okay. Any other questions on chapter 3? Before I move to the ones in chapter 4? And it's a pretty good one. That encompasses everything. I think that's the hardest. The harder ones. Okay. So in chapter 4, the request was 16 and 39. Let's see what those look like. Oh, one of these. Okay, yeah. Yeah, that one's tough. Okay. 39. It's 39. Is 39 statically indeterminate one? I think it must be, right? Yeah, it must be. Let's see how bad that one is. Okay, 39 is pretty easy. Okay, so let's do, this is not a problem. So that's good. Let's do 16. 16 is probably I think the harder one out of this group, just because it's spatially a little more challenging, I guess, right? But these are actually, the difficulties we got with 416 are actually, I think they're really good for engineers to deal with. It's a good stretch problem, right? A lot of times, I know you guys probably don't believe this, but professors try to give you easier problems to solve because, too jerky on those things, but what makes problems, one of the things that seems to make problems really difficult for people to solve, and this is not just students, this is everybody, is, when they're confounded by these sort of more complicated geometries. And this is a good example of this. So the concept in here is still the same stuff, right? This is just a straight up elongation problem. There's really nothing else going on here, but it's got springs. And so that makes it a little bit confusing, right? So when you see this, right, whether it's something geometrically kind of confusing like this because it has the springs, or maybe it's one of those problems where you have a gap and you have to. So what you really want to do is you want to think very carefully about, kinematically or geometrically what's going on here. Okay. And also, draw more free body diagrams, because that's sort of the key that like unlocks the door to a lot of these problems. Okay. Sometimes you have to do more than one, or even sometimes more than two free body diagrams. All right. So here they you have this coupling rod, 5 kips, determine the distance. Okay, they want to figure out that. I want you to find this distance. Okay, so when no load's applied, right? When the force is 0, we know that D, the unstretched length, is 10 inches. Okay, and they want to know what D is after the load is applied. D equals 5 kips. Then after it's deformed, what's D? All right. So what's going to happen here? Okay, so all right, this is a little. So we've got this sort of compression string. Determine the distance D between ceiling. Okay. So they're kind of giving you a little bit of clue here. The spring is going to change length because it's a spring, but also they're saying you should consider the fact that the bolts will elongate because they have load in them. All right. You can't like assume that they're rigid. All right. Okay. All right. So plates A, B, and C are rigid, and they give you the spring stiffness. All right. So what's a little bit hard to see here, I think this is, like if we zoom in on this, like there is a gap here. Okay. Oops. I don't know if that's part of the confusion or not, right? But this shaft here is not connected to this bolt. Okay. Even though it looks like it is. There's a small gap here, okay? And that's kind of critical because, as you pull up here, right, that's going to take this plate B, compress it up into the spring, right? The spring is going to put a force onto plate A, and then that's going to be resisted through plate C and the bolts with the balancing 5 kip force. All right. So we should draw the free body diagrams that give us the force in the spring, right? We need the force in the spring. Why is this thing? I think it's zoomed in. What is going on? Something weird happened here. Cut this again. Yeah, zoomed in. Whoa, Jesus. All right, this when I zoomed in, I guess I just made this thing so ridiculously big that it's causing a problem. Can I make it small? gotta be a way I can make this smaller. We could do. All right, well, whatever. I guess I'll do it this way, but now my pen is so thin. Let me see. I guess I have to do it thicker. Yeah. All right, that's okay. So right. So we're gonna have to figure out use a free body diagram to figure out the force in the spring, as well as a force in the bolts. Okay, this is not a statically indeterminate problem, right? So let's look at the free body diagrams, right? So right on this bottom plate let's look at plate B, right? You have the force acting up, which we know is 5 kips, right? And then we also have balancing that, the force from the spring, correct? And I'll put half on each side. And that's the correct free body diagram on that, right? I mean, there's really nothing else acting on that. The bolts don't act on that. Plate B slides along the bolts, right? So that's the only thing going on there, right? So you can see here, this, again, by drawing this free body diagram, you don't have to kind of try to guess where the force is distributed. Here, it's pretty clear that the force in the spring is 5 kips, correct? All right. Now, let's look at the top plate A. So I'm going to draw that free body diagram, right? So the top plate A has the spring force acting on it, the net spring force acting up, because it's in compression. We know that that's 5 kips. And then balancing that is going to be the force in each bolt, right? So there's 2 of those, right? So the force in the bolt is half of the force in the spring, or 2.5 kips, right? And the force in the spring is 5 kips. Obviously, the force in the spring is a compressive force, and the force in the bolts are a tensile force, okay? All right. So now, I can figure out the compression of the spring and the elongation of the bolts, okay? So we know, let's figure that out. So this is the compression of the spring. Let's figure that out. So we know that is the force divided by the spring constant. So that's the force of the spring divided by the spring constant, right? And it's, it's going to be a negative number. So, we'll put a minus sign in there. So that's 5 kips over K, which is 12 kip inches. And so obviously that gives me units of inches. So 5 over 12. So that's 0.417 inches compression, right? It's and now we can also figure out the elongation of the bolts, right? So the elongation of the bolt is the force in the bolt times the length of the bolt over A times E, right? And so it's steel, so we know that E is 30 times 10 to the 6th PSI, right? And the cross-sectional area, what is it? It's each bolt is a 1/4 inch. And so that area is 0.0491 inches squared, right? So we can get the elongation of the bolt. Again, that's going to be elongation, right? Because the force is a tensile force in there. You can see that from the free body diagrams. And it's 2.5 kips, because there's, from this free body diagram, shows you that. The length is well, yeah, the bolt length, is going to be this full 6 inches, right? You don't have to subtract off the plates. A is the 0.0491 inches squared, and then E is the 30 times 10 to the 6th PSI, and this will give me an answer in inches. All right, so I get 0.0102 inches, and that's a positive number. It's an elongation, okay? All right, so now I know that. Well, now we have to just kind of go through the geometry, right? So now we can just go through the geometry and figure out what that means to D, all right? So, oh, do they want us to take into account the elongation of this as well? Ooh, they do. Somehow I feel like, wait, do we need to? Oh, no, we can't because they don't give us the area on that too, right? They give us the 8 inches to figure out the unstretched spring length. Okay, right. So yeah. Okay. All right. So again, this is kind of a good trick for doing these sorts of things, and actually you can use this in a lot of stuff, right? It gets a little bit confusing. Like, do I add? Do I subtract? So you can kind of think about these things in the limit, right? So let's first imagine that the bolts are rigid. Okay, so the bolts are rigid. They don't change. The spring compresses. So what's going to happen to D if the spring compresses? Does it get longer or does it get shorter? The spring compresses. Does D increase or decrease?
Increase.
It'll increase, right? You can look at this. Does that make sense? I know it sounds a little bit weird, but that's where, you have to look at it geometrically to see what's going on. So the spring compresses by negative 0.417. So we really want to, so the change in length, right, is going to equal minus the delta of the spring. Because there has to be a sign change, because you just told me when the spring compresses, when it's negative, D increases. Okay. Well, let's do the same thought experiment for the bolt. Forget about the spring. The spring is now infinitely rigid. If the bolt stretches, what happens to D? Does it become bigger or smaller? Bolt length increases. This bolt gets longer. Does D get bigger or smaller?
Bigger.
It gets bigger, right? It's going to get bigger, right? Because basically you can think of it like this plate here is going to stretch down, right? So that means we would do, so the elongation of the spring, the elongation of the bolt has the same sign as the elongation of D, right? So we're going to add that here, right? So maybe you got confused and you say, okay, do I add the bolt elongation onto the spring or do I subtract them, right? Doing this, right? This is basically like superposition in a sense. Two things are changing, but you fix one and figure out how much it changes due to the one factor, then do the same for the other factor, and then you can add them together, or you figure out what's the relationship, right? So in this case, it's going to be minus the elongation of the spring, which is a negative. So it's going to be 0.417 inches plus the bolt, which is the 0.0102. So if you did add them together, that is the correct answer. And that is 0.4272, I guess, right? Inches, right? Positive. That's the that's how much D changes. You should add that onto the original D, which we got to do a little. What do we got to do here to figure that out, right? I don't know. Do they give you D initially? They do, right? D is 10 inches, right? So D becomes 10.427 inches, right? Does that make sense? All right. Two things though. Again, good problem. You know, what are the forces in the spring? What are the forces in the bolt, right? You know, don't let all these sorts of questions confuse you as to how to start the problem. You have the tools that allow you to dissect the problem. Free body diagrams. I mean, those easily show you how the external force is related to the force in the springs and the force in the bolts. And it's not confounded by how much they elongate or anything like that. It comes out purely from the free body diagrams, okay? That allows you to figure out the stretch in the spring and the elongation of the bolts. Then similarly, how do we combine those elongations geometrically to give you D? You know, you can use this sort of like thought experiment in a lot of things where you hold one factor fixed and see how the quantity you want changes with respect to the other factor, and then flip it. And then you can figure out whether they add or subtract easily, okay? All right. Let me clear this out because I don't know it. This got weird with the Zoom stuff. Okay, so the next one was 439, which I think is actually a pretty easy statically indeterminate problem, but it's one of the cases where the compatibility equation is not quite as straightforward as just, you know, the elongation is 0 or the elongation is equal. This is that. I think actually I did discuss this in class really quickly, but actually I don't think I pointed to the problem specifically. So here we go. And I think I might have talked about the other one, and this one's a little complicated just by the fact that it's a design problem, I believe. It's supposed to just like calculate the elongation. All right, so this is this sort of crane problem, right? So it's statically indeterminate because we have the two wires here that are connecting the dead load, right? This is 2,000 pounds, right? Back to the crane at point C and B, right? One of the wires is a little bit longer, right? Wire AC is 40 thousandths of an inch longer than wire AB, all right? So in this particular problem, it's a little different than its friend 438 because it wants you to figure out the cross-sectional area in AB such that the force in AB equals, well, let's use N. We should use N to be consistent, right? The force in wire AB equals the force in AC. I mean, it's not always going to be the case, but this is what you want, right? This is the want, right? Okay. Do they give us the area? They give us the area of AC, and obviously they give us Young's modulus here. All right. Oh, and it yields. Okay, so we got the yielding problem. All right, so they've gotten it. So they really kind of made this complicated because they also, you know, maybe it doesn't yield, but I almost bet it does yield because otherwise they wouldn't have given you that in a problem, right? Like obviously in real life, you're given all the information whether or not you need it or not, but in problems they always kind of tip their hat by giving you that information. Okay, so you got so actually something's going to yield, right? All right, and this is statically indeterminate. So, you know, the free body diagram here is pretty straightforward. Although there's a couple of ways to do it, we can draw the free body diagram of that block here, right? Don't know why it looks like that. So down we have the 2,000 pounds, and then up we have the force due to the wire AB, and the force from wire AC. And so here we just have that NAB plus NAC is equal to 2,000 pounds, right? So this is our equation of equilibrium, but we have two unknowns, all right? All right, so we need a compatibility condition. So in this particular case, right, I'm going to exaggerate it. So this is wire AC, and here is wire AB. And initially, there is a length change here. I mean, not a length change, but initially, AC is a bit longer, right? By 0.04 inches, right? AC is a little bit longer. So what happens when you load this up is first, AB is going to stretch 0.04 inches, and there will be no stretching in wire AC. Then at that point, after AB stretches the 40 thousandths of an inch, now they're both the same length. AC is going to tension up and then start to stretch, okay? So that means the elongation of wire AB, what am I doing? The elongation of wire AB has to equal the elongation of wire AC plus 40 thousandths of an inch. And again, this is one of those ones you're like, you get confused. You're like, okay, should it be plus 40 thousandths of an inch or minus 40 thousandths of an inch? It's like a pretty easy one to kind of flip. I always make sign errors all the time. So I'm going to check and just make sure. So I'm going to do another thought experiment, okay? So like, let's look at this sort of condition, right? So if wire A, right at the point where wire AB stretches 40 thousandths of an inch and wire AC has not stretched at all, does this equation hold? So what I'm saying here, wire AB has stretched 40 thousandths of an inch, so delta AB is 40 thousandths of an inch, and delta AC is 0. Is that satisfied by here? Yes, it is. If I had put a minus sign here, it would have been wrong. You know what I mean, right? So that's how you can check, or that's like how I sort of try to do a check, So this is good. So now I got this compatibility condition, right? Now we need to get this in terms of the forces, right? So why don't they give us the yield? They don't give us any post yield. Still confused why I don't know why they gave us the yield, because I'm betting it's going to be below yield because they don't give us anything about they don't say whether it's perfectly plastic or anything. So okay, well, let's figure it out. Let's not worry about that. All right. So we know that the elongation of AB is going to be the force in AB plus the length of AB, right? Which is the length in AB is 60 inches, right? And the length of AC is 60.04 inches, right? All right, and that's over the cross-sectional area, which we know, right? AB, we know. No, we know AC. We don't know AB. So this is our unknown, AB, right? And we know E, that's E of the steel, right? All right. That equals the elongation of AC, which is going to be NAC length of AC, which we know, over the area of AC, which I actually also know. Does it give it to me in terms of area? Yeah, it gives me the area right there. And then E of steel plus 0.04 inches. All right. Well, actually, I think this is actually easier than what I'm making it out to be. So let's just sort of step back and see where we're at. So we have our compatibility condition in terms of the forces. We have our equilibrium condition in terms of the forces. And we also have this other design requirement that the two forces are equal. Well, you know, if the two forces are equal, right? If the two forces are equal, this is immediately going to tell me that NAB has to equal NAC has to equal 1,000 pounds, correct? From here, right? Okay. So I actually could put that into here and here. I know the lengths. I know Young's modulus. I know this area, and I just don't know that area. So I can use this directly to solve for that, okay? So, right, we put numbers into all this, right? NAB is 1,000 pounds. Length AB is, why is it do that? Length AB is 60 inches. The cross-sectional area is the unknown. And then the steel is 29 to the 6th, right? And that equals NAC, which is also 1,000 pounds. Length here is 60.04 inches. A here is 0.02 inches squared. That's given. And then this is 29 to the 6th PSI. And then 0.04 inches. So from this equation, I can solve for the area of AB, okay? Now, I guess what I'm confused about is why they give me the yield stress, because if they go plastic, I don't know anything about the post-yielding behavior. They don't give me any information there to figure out, you know, if they gave us the stress strain curve and we knew something about what was going on post-yielding, I could do something about this 70 KSI yield condition, right? Like if I'm up here, I don't know whether the curve looks like that or that or that, right? Does that matter? Well, no, I guess it doesn't matter because they both have the same material response. And they're telling you that you have the exact same load in each one. Oh, but the area is different. Yes, the area could be different. So your stresses could be different. Yeah, your stresses could be different. So what, did anyone figure this out? What's the area AB? What, calculate this real quickly. What does this turn out to be? I'm gonna make me do it. Why doesn't somebody else try to calculate this out? Because I'll probably screw this up.
I got 0.103.
Did anyone else get that? Not that I doubt you.
Wait,
but
I missed to add
it's-
the 0.4. So it's 0.43. 0.143. Sorry.
That's it. Did anyone else get that? Let's just do it real quick because I want to know. I just kind of curious. I mean, this is kind of irrelevant for this for the exam, but probably wouldn't be bad. Just I should know how this problem goes. Enter. So this number here, right? I got this to be 0.104. And then we add those to 0.04 added on top of that. So this whole thing is 0.144 inches. And then let's, whatever, figure out the 1060 and divide by that, right? I shouldn't do this because I'll probably get the wrong number and then just delay everything, right? So we got that. Let's swap. I'm off by a decimal place. Is that possible? I got that.
Me too, sir.
What's that?
Yeah, I got that same thing too.
That it's 0.0144, not 0.144, right? Is it? Or did I screw up? Is it A or B? What else to say? Well, if it's B, B would be the worst case scenario. Let's figure out the stress in this thing. So if we figure out, so B is the smallest diameter. So let's figure out the stress in AB. And I hope it's less than, otherwise I'm going to be at a loss how to do this problem, to be honest with you. We know that the force is 1,000 pounds. And if that's the area, and I'm going to pick that because it's the less area. So that's the worst case situation. This gives me, oh yeah, it just comes under. This gives me 69 KSI, which is less than 70. All right. And then obviously the other one is going to have an even lower stress, same load, bigger cross-sectional area, right? So yeah, so okay, so this in this particular case, that number doesn't mean anything, but because we're less than that, right? So it's actually one of the few times where they gave you an extraneous piece of information, okay? All right. All right, so yeah, again, this is a little bit of a different wrinkle, but it's not a big deal. It really shouldn't be that big of a deal if, again, you kind of write down in an engineering standpoint with the equations, using free body diagrams, compatibility conditions, and putting in for the, the elongation equation, what information do you have, what information you need, right? It comes out pretty well, okay? Any questions on that?
Professor, just one question.
Yeah.
On the compatibility equation.
Yeah.
I'm having trouble understanding why it's AB equals AC plus 0.4 instead of AC equals AB plus 0.4.
Okay, all right. Okay, so it's saying, so we're good with this, right? Here, that AC is a little bit, is 40 thousandths of an inch longer than AB. Unless I got that wrong. Yeah, AC is 40 thousandths of an inch bigger than AB, correct?
Yes, sir.
All right. So when we first apply the load, like even 1 pound of force, right? Imagine we gradually apply the 2,000 pound force. Well, what's going to happen first? I mean, it's a wire, so you can't put a wire into compression, right? It only sees tensile load. So the first thing that's going to happen is wire AB sees all the force, correct?
Yes, sir.
So it's going to take all the force until it stretches to the same length as wire AC. Now, once that happens, wire AC will also pick up some of the load. And the two will now stretch afterwards, okay? So wire
Yes.
AB first has to stretch 40 thousandths of an inch, okay? So that means like you can, again, do it through a thought experiment, right? So right at the point where AB has stretched the 40 thousandths of the inch and AC has not changed, right? So we know at least at one point, delta AC is equal to 0 and delta AB equals to 0.040 thousandths of an inch, right? Forget about the forces, but kinematically, when we just immediately start to tauten up wire AC, this is the displacement condition, right? That has to, the compatibility condition has to satisfy that, or have to be satisfied that. Does it? Well, if delta AC is 0, right? If this is 0, AB, yes, it does equal 40 thousandths of an inch. So it's correct. Does that make sense? Like, it wouldn't be minus, right? I mean, that's the other confusion is like, should it be plus or minus, correct? And it has to be plus because of, this condition. Or, if you see it obviously just by talking about it, that's fine as well. But I know sometimes it can be a little confusing as to what the sign should be, all right? Does that make sense?
Yes, sir. Thank you.
Any other questions? How about if anyone has a question on something in chapter 5, that would be good. It's not a statically indeterminate problem, or something, something that will be on the exam.
For chapter 5, Professor, are we going to do angle of twist material? Because in the announcement you said you weren't going to put it in there. It was only going to cover sections 5.1 and 5.2.
Isn't 5.2 angle of twist? Or did I do that wrong? Okay, well, you know what? If I said that, then I'll do that, okay? Okay?
Okay, so it'd only be 5.1 and 5.2? Because, yeah, you said no torsion material or the angle of twist material.
Let me just, okay, this is kind of important. I probably screwed it up. Let me make sure I get it right, okay? So, and let's do whatever's in the announcement, okay? Let's be consistent. Oh, you're right. Wait, angle of twist is like 5.4, right? Okay. Let me just check real quick what the announcement was. I probably deleted it, right? All right. Just a second. I'm sure you're right. I just want to I just don't want to screw it up any more than I've already screwed it up. I don't know why my internet is crazy slow today. Oh, you're right. Yeah, I said 5.1 and 5.2. Okay, so thank you. So yeah, so no angle of twist, just the torsion equation, right? If I give you some, so these will be like super easy, right? So only, problems statically determinate, right? Maybe something like, at worst case, it could be something like this, right? Like the problem we did last class with the gears, right? Where you had I forget which one that is, right? But we had like oh no, but that was an elongation. That was a angle of twist problem. But anyway, it would be like a problem like that. right? Where I give you the torque here, the torque here, the torque here, the torque here. And I would ask you to find, you know, what's the shear stress in this segment, or possibly like find, you know, it's a solid shaft, find the outer diameter given an allowable stress. Does that make sense? Things like that. Yeah, but no angle. I won't give you any angle of twist then. Okay. Yeah. Thanks for letting me know. Sorry about
Okay,
that.
thank you, Professor.
Do allow. I don't know why. That's diameter outer given an allowable stress, right? So it could be like a design type of problem or just a straight up analysis type of problem. Okay.
Okay, thank you.
Any questions on that one? Either stuff from 5.1 or 5.2.
Can we just do one, just in general? Just
Let me just
Any of-
roll, spin the wheel of Hibbler.
yeah, just on that concept.
All right, let's find a good one. All right, let's find it. Let's find. And so I didn't even say 5.3, so that means no power transmission either. Okay, so even though those are pretty easy, but you know. Okay, let's find that one. Let's find a design one because those are gonna be more challenging. Let's find a good design problem. Like where they give me an allowable stress. And I want to find like a diameter or something. These are all really easy. The only design problems they're giving you are like find the maximum torque, but that's really not even, that's not, those are simple. I want to see one where you have to find one of the diameters. There's gotta be one like that. I think there's one with power. I could do that. That's not bad. Okay, let's do this one. Let's do 5.14, even though it does it in terms of power. And I said, you know, you're not going to be responsible for power, but whatever, you know, it's easy to calculate the torque from the power. This is not a big deal. Okay. But this is probably, you know, like these design ones are always going to be kind of the more challenging ones to do. So let's do it. All right, so we have a steel tube. They give us the outer diameter. The outer diameter is 2.5 inches. All right, we know that it transmits 9 horsepower at 27 RPM. So again, I won't ask you this, but you know, obviously we can use this to get the actual torque. They give us an allowable shear stress. The stress has to be less than or equal to 10 KSI. And what we need to do is find the inner diameter to the nearest 1/8. You know, we can only buy these in 1/8 inch increments, okay? All right. So let's first figure out the torque, right? So the torque is going to equal the power over the angular speed. But we got to do the unit conversion here, right? So we have 9 horsepower. And if you remember, each horsepower, there is 6,600 pound-inches per second per horsepower, right? All right. So that gives me the power in pound inches per second. And then we have the angular speed as 27 RPM. And we want to get that into radians per second. So there is 2 pi radians for every revolution. Okay. And there is minutes downstairs. So there's 60 seconds in every minute. Okay. And so this will give you the answer just in pound inches, right? So I get, this is 2.8 radians per second. And then I get the power as 59.4 kip inches per second. And so if I divide these two, that gives me the torque is 21 kip inches. Okay, so now we know the torque. All right. All right, so now we can do the design problem, right? So I don't know J, right? J is pi over 32 outer diameter to the fourth minus inner diameter to the fourth, correct? I know the outer diameter, but I don't know the inner diameter. All right. The shear stress is equal, the maximum shear stress is the torque, the 21 kip inches, times the outer radius over J. Well, they're kind of nice because they gave us the they gave us the outer diameter. So I know that the outer radius is 1.25 inches, right? Just half the outer diameter. And so I know that this stress has to be less than or equal to the allowable stress, correct? So this can allow me to solve for J, right? So J needs to be greater than or equal to TC over my allowable stress, correct? So that is equal to 21 kip inches. C is, I don't know why that is moving. C is 1.25 inches. That's the outer radius, right? And this is going to be over the allowable stress, which is 10 KSI. And so this is going to give me, I got a K upstairs and downstairs, so they'll cancel out. This is going to give me an answer in inches to the fourth, right? All right, so I get here, J has to equal, well, or J has to be greater than or equal to 2.63 inches to the fourth, all right? So the worst case, so let's figure out what the inner diameter would be in that situation, right? So we know that pi over 32 outer diameter, we know the outer diameter, right? That's the 2.5, right? Oops, what am I doing? This has to be greater than or equal to the 2.6, right? So this has to be greater than or equal to. So we can just solve this for the inner diameter, right? Now we have to do the rounding, but let's find out the inner diameter from this, right? So the inner diameter to the fourth power, I'm going to just do it in the limit case for now, right? So that is gonna be. Well, there's a negative here. Right? So, 263. 32 times pi divide. And then 2.5 to the fourth. Here's my fourth maybe. Here's wrong. What am I doing here? I always get this confused up. Let me do this. Let me just get this right. So minus di to the fourth has to be greater than or equal to 32 pi 263 h to the fourth. Right? Okay. And that equals all right. This is 2.6. Let's do this. 2679 inches to the fourth. All right. So, and then here I got the 2.5 inches to the fourth. So this number here is 39. Is that right? It seems small. 39.1 inches to the fourth, right? And so, why is that? Oh, I dropped a decimal point. Oh, what am I doing? Sorry about that. That's why, because that's 2.6. So this is that, right? Okay, that makes sense. Sorry about that. That's why I was coming out goofy. Okay, because then, this minus the 26.79 inches to the fourth, that has to be greater than or equal to the inner diameter of the fourth, right? This number now becomes 39.1, 26.79 minus, so this is 12.3 inches to the fourth, greater than or equal to di. So let's take the fourth root of that, right? And I get this to be 1.87, right? And this is, there's inches in there, right? Okay, so the diameter, the inner diameter has to be less than or equal to 1.87 inches, right? So we need to round it off to the nearest eighth of an inch or quarter of an inch. What do they say? Eighth of an inch, okay? So that would be, so 1.875, right? That would be the nearest eighth inch. But you can see the problem with that is that's actually, di has to be less than this number, and that doesn't work. So we need to round down another eighth of an inch. And so that's going to give me 1.72, wait, 1.75, right? 1.75. So that's the correct answer, okay? All right. And it makes sense too, right? Because obviously, you know, if you make the inner diameter bigger, you're gonna, make the stresses go up. So we're gonna, when we round, we have to always round so the inner diameter gets smaller, right? Or the outer diameter gets bigger, okay? All right, any questions on that? All right. Well, okay. I guess that's the end of class. So if somebody has another quick question, I could kind of respond to it, or if not, I think that's probably it, right? Oh, what happened? There we are. Okay. All right. All right. Well, have a good weekend, and we'll see you Tuesday.